And here we go. All right, so intermolecular forces and their properties. So just quick recap that the word IMF is abbreviated for intermolecular forces, just for expediency's sake. These are our three intermolecular forces, so you should already have those in your notes. You don't really need to write that down. The strength of the intermolecular force you should also have down, and that is the primary thing that affects the properties of the substances. The more intermolecular force a substance has, the difference it's going to affect the properties. And the last thing is that it takes energy to break intermolecular forces. So if you think about magnets, to pull a magnet apart, it takes energy to do that. And the more that the magnets want to stick together, the more energy it takes to pull it apart. And likewise, when they come together, energy is released. So a lot of this can go into when we think about the changes in state. So we're talking about melting point, we're talking about boiling point. When we are melting things, think of things going from a solid where everything is packed tightly together versus a gas when the molecules are separate and flying around independently. Well, you had to pull those things apart. So the stronger the IMF, the more it sticks together. The more it sticks together, the more energy it takes to pull it apart. And so that last statement down there that's highlighted, that's really the thing that you need to know, that the stronger the IMFs are, the higher the melting and boiling points are going to be. And this becomes very interesting when we think about water. So water is really small. It has a very low molecular weight. And in general, small molecules have really low melting and boiling points because they're so tiny, they're not going to stick together that well. Things that are very light are very easy to manipulate. Just think about, manipulating a box full of packaging peanuts versus a box full of bricks. Things are light, they're easy to move around and manage. And based on its size, if you compare water to other relative things, water should be a gas at room temperature. The fact that we have liquid water is not kind of how it's supposed to be, but it does because water's IMF is hydrogen bonding, which of course is the strongest of all the IMFs. And because it has hydrogen bonding and because it's so tiny, it really creates this intense network of attraction, which makes its melting point and boiling point so much higher than you would ever predict. If water was all of a sudden this brand new substance, we would never predict it would have the properties that it does. But it does because the IMF of water is so incredibly strong, which is important because we obviously need water to exist. All right, so let's look at the first property, which is called viscosity. So this is just terminology. Viscosity is the resistance to flow. So think about, a thick syrup. When you pour it upside down and it just takes a long time to flow, it's resisting that motion. So things with a very high viscosity are thick. They're kind of sticky. Things with a low viscosity are very runny. And so the more the molecules stick together, the stronger the IMF, the higher the viscosity. So we can think about something like, molasses is always like the typical example, but how many people know what molasses is? But think of like a maple syrup kind of thing, versus, if you've ever experienced it, oil. They have very different viscosities, and we can look at them and look at their IMFs in order to explain why that is. So this also works with large molecules. So typically, one of the good examples is like the black tar that we use like for roads and asphalt. That's oil. That's a non-polar molecule, but they're humongous. And so because it's so big, not only does it have more electrons, which makes those London forces even stronger, but they're able to just kind of mix together, like a ball of Christmas lights, and just like form this knot, and the molecules kind of get locked in because they can't really move around, and as a result they stick together. So again, molasses. If you don't know what molasses is, it's really gross. All right, next property is surface tension. This is the resistance of a liquid to spread out. So think about a droplet of water sitting on the table versus a drop of nail polish remover. So if you have nail polish remover in your house, I only say that because oil is a little bit messy to clean up. Put a drop of nail polish remover on the counter and then put a drop of water next to it, and you're going to notice a significant difference between the two. And the reason, again, is IMF. So the more IMFs, the more they stick together, the more they are going to resist spreading out. So again, thinking about this in terms of magnets is always going to be a little bit helpful. So we're looking at things flowing or surface tension, things wanting to stay together. The more attraction, the more IMF, the higher the surface tension. And the last thing we really want to talk about is soap. Soap is kind of a unique molecule in this because it has different intermolecular forces going on. Soap is a class of compounds called surfactants. And what it means is they have a part of the molecule which is polar, so this is what the polar head is, and they have this long non-polar tail. And so they're able to interact with a almost unlimited number of things. Because the polar part will bind to water or other polar compounds, and the non-polar part, the tail, will bind to non-polar things. And so it makes it just a really good cleaner and all sorts of things. So all of these things you're going to want to have written down just to kind of talk about how soap works. And how soap interacts with water. And so a lot of this, I already just said that the soap has a polar head and a non-polar tail. And so it looks kind of like this little pin cushion, or like a fabric pin. I don't know what they're called. A pin that you use like in sewing. And so one part can interact with the water and the other part can interact with dirt and grease, which is non-polar. And so what happens when you are washing your hands, which of course we should all be doing quite often these days, is that the soap can actually surround the dirt, so the non-polar part. And this is called a micelle or a micelle. And so if you look at this, this becomes its own little unit. And the outside, this becomes like a little sphere, because there's also things coming at you, is just the polar part. And so the water can kind of come in and carry it away. In the example of COVID, what happens is the soap actually interacts with the membrane of the virus, And so when you're washing your hands, the soap molecule binds to the membrane of the virus, and when you wash it away, it actually rips the virus open and actually completely destroys it. The same is true with rubbing alcohol, and all of our different disinfectants. That's kind of how they do it. They just kind of take the skin of the virus, so to speak, and they just kind of rip it apart. Kind of interesting. And so what happens here is that the soap disrupts the ability of the water molecule to kind of stick together. And so the surface tension of the water is lowered when the soap is added. And this allows your water to kind of go everywhere. All the little nooks and crannies in your hands and little skin folds and stuff allows that water to get in there and actually flush everything out. Or as I wrote here, looking at your dirty dishes and just be able to cover and really clean off that entire plate.